Okay, buffer solutions. So first, a definition of a buffer solution. A buffer solution minimizes changes in pH upon the addition of a small amount of acid or base. Okay, so that's the definition. If you take a beaker and you've got some water, just simple water in there, and you add some acid, then the pH will drop dramatically, will drop a lot. If you have a beaker of water and you add some alkali into there, the pH will increase dramatically. But that doesn't happen when you have a buffer solution. If you have a buffer solution and you add some acid, the pH will change very, very slightly. Very, very slightly. And similarly with alkali, the pH hardly changes. However, the pH does not remain constant. It does change, but very slightly. Okay, so that's the definition. Buffer solution minimizes the change in pH upon the addition of a small amount of acid and alkali. So what do you need to know? You need to know how to make a buffer solution. How to make a buffer solution. How to make a buffer solution. Okay, so a buffer solution has got two things in it. It's got a weak acid. You take a weak acid, and our general symbol we use for weak acid is HA. So for example, ethanoic acid is a classic example. Okay, so you take a weak acid, symbol HA, like ethanoic acid, and you take the conjugate base. So basically we mean A minus. So we mean, if it's ethanoic acid, we mean like that, the ethanoate ion. So basically it's the salt of weak acid, the conjugate base, right? These two things together, the weak acid and the conjugate base, that's how you make a buffer, right? So you can take, if you've got your beaker, okay, you can put your weak acid in there. Now normally you use the same volume, the same amount of each. You put your weak acid in there, and then you put your salt, your conjugate base, sodium ethanoate. You put your sodium ethanoate in there, stir it up, and that is your buffer. A second way to make a buffer is that you have your weak acid, but you have more weak acid. So you have more weak acid, ethanoic acid, and this time you add sodium hydroxide, and that makes, when sodium hydroxide reacts with ethanoic acid, it makes sodium ethanoate. So then you've got to get your proportions careful. Then you have your weak acid, and then you have your salt of your weak acid. Okay, and you normally have an equal concentration. In a buffer, you normally, not always, but normally have an equal concentration of weak acid and the conjugate base, normally. Okay, so that's how you make a buffer solution. How does a buffer actually work is our next one. How does a buffer work? Okay, so how does it work? How does a buffer work? Right, so you've got two things in a buffer solution. You've got the weak acid, which partially dissociates into ions. Okay, this is all aqueous. I'm not just not writing the state symbols on, but it's all aqueous. Okay, and then you have your salt of your weak acid. So maybe the sodium salt. And a sodium salt in water will fully dissociate into ions. Fully. Like that. Okay. So the example that I'm going to do, I think I'm going to do it in an actual example, right? So if we take ethanoic acid, ethanoic acid will partially dissociate into ions, plus H plus, yeah? And then if you take the salt, CH3COONA, and that will fully dissociate into ions. So CH3COO minus plus Na plus. Okay, so that's just an example. So this is how a buffer works. You've got weak acid which partially dissociates and a salt which fully dissociates. And there's an example with ethanoic acid. Right, so a buffer, the basis of a buffer is the fact that because hardly any acid dissociates, there is a lot of this in the buffer, okay, because hardly any dissociates. Because a salt, the conjugate base, fully dissociates, there's a lot of this in the buffer. Okay, and we say a large reservoir. They use the term a large reservoir. It just means a lot. A large reservoir of A minus and HA. All right, so basically, in a buffer, what you have got is you've got a lot of this and you've got a lot of that, in summary. And that's what minimizes the change in pH. So if you add an acid, and it only works for small amounts. If you add a lot of acid, it won't work. Add a small amount of acid. Okay? If you add a small amount of acid, the acid concentration here is going to increase. Yeah? So the acid concentration will increase. If you add acid here, concentration increases and the position of equilibrium will therefore move to the left to minimize the change. That's using Le Chatelier's principle. You add some H plus, the position of equilibrium moves to the left to minimize the change. I'm just going to write POE, which means position of equilibrium, moves to the left to minimize the change. To minimize the change. Okay, which moves to the left to minimize the change. Okay, but that's all okay. That's okay. This is all okay. It's okay because we have, if a position of equilibrium moves to the left, there is a lot of HA. So a little bit more HA is not going to make a difference. If you have £100 and you see a penny and you think, well, I've got £100, a penny is not going to make much difference. So when you've got a lot, a little bit more doesn't make a difference. But if you had 10p and you saw a penny, then that would make a lot of difference. So it doesn't matter, okay? Then when you add a small amount of alkali, what happens? How is the pH minimized? So if you add a small amount of alkali, what happens? So alkali, OH minus, reacts with acid to make water. Okay, so if you add a small amount of alkali, it'll react with the acid. So therefore the acid concentration will decrease because you're using up some of the acid here. So the acid concentration will decrease. So if the acid concentration decreases, the position of equilibrium, Le Chatelier's principle, if the acid concentration decreases, the position of equilibrium will move to the right in order to restore the equilibrium. So the position of equilibrium will move to the right. Moves to the right. Okay, so this is how, and this is okay. Again, it's okay if the position of equilibrium moves to the right, because you have a lot of this. So if a little bit more is made, that's okay. If a little bit of this is used up, that's okay, because you've got a lot of it. You've got large reservoirs, so a small change doesn't make a difference. So in summary, let's just summarize. If you've got a weak acid, a buffer, sorry, with a weak acid and the conjugate base, okay, if you add alkali, then the position of equilibrium moves to the right. If you add acid, then the position of equilibrium moves to the left. That's just in summary, okay? So adding alkali moves it to the right, adding acid moves to the left. So that's how it works. Next, you need to be able to calculate the pH. So how do you calculate the pH of a buffer? Okay, so calculating the pH, of a buffer solution. Okay, calculating the pH of a buffer solution. Okay, so let's just remind again. So a buffer solution is a weak acid, and you've got the salt of the weak acid, the conjugate base, which is fully dissociated. Okay, now you can write Ka for the weak acid. Ka is Ka is H plus times A minus, square brackets, remember it's all square brackets, and then HA, like that. Okay, now remember what you do for the pH of a weak acid. When you're working out the pH of a weak acid, we use the approximation that H plus equals A minus. Okay, so for a weak acid, we say that equals that. But we can't say that anymore because there's that involved as well. So H plus does not equal A minus because you've got this from the salt, from the conjugate base. So these two are not, so you cannot say this for a buffer solution. Okay? But can you see, because we have a lot of this, a lot of weak acid, because hardly any dissociates, we've got a lot of A minus, that we can say that this is the concentration of the salt, concentration of the conjugate base. This is the concentration of the salt, and we say that this one here is the concentration of the acid. And that's how we work our H plus. So let's give an example. So say you were asked to calculate pH of a buffer solution, right? And the buffer solution contains 0.1 concentration of the acid, the weak acid, and it also contains 0.3 concentration of the salt, the conjugate base. Okay, that's your buffer. And Ka, they tell you Ka as well, you give you that information. 1.74 times 10 to the minus 5 is Ka. And your job is to calculate pH. To get pH, we need H plus, don't we, to get pH, all right? So we've got Ka, that's been given to us. So Ka is 1.74 times 10 to the minus 5. Ka is H plus times the CH3CO minus over the acid. Okay, so the salt, this is the salt, 0.3 will go there, 0.3. This is the concentration of the acid, concentration of the acid 0.1 will go there. Okay, so your calculation is going to be 1.74 times 10 to the minus 5 equals H plus times 0.3 divide 0.1, because your 0.3 is there, your 0.1 is your acid, and then you rearrange and you get your H plus. So when you're rearranging it, H plus is going to equal 1.74 times 10 to the minus 5, and it's going to be times 0.1 and then divide by 0.3. Divide by 0.3. And when you do that, H plus comes out, what does it come out as? 5.8 times 10 to the minus 6 is your H plus, and then you just go pH is minus log H plus, so you minus log it to get your pH, and the pH 2 decimal places will be 5.24 in this example. Okay, so in summary, to work out the pH of a buffer, you say that the A minus is the concentration of the salt, and the HA is the concentration of the acid, because we've got a lot of weak acid and we've got a lot of A minus. Okay, another thing on this calculation point is, if we just go back again, let's just go back to Ka. Ka is the right hand side, the products over the reactants. Okay, right, so if the concentration of the salts, the conjugate base, equals the concentration of the acid, okay, so if these two equal, then what you could do is you could cancel them out because they're the same number, and then that would mean Ka equals H plus, and therefore if you minus log both sides, you can say that pKa equals pH, because you do minus log Ka minus log H plus, pKa equals pH. So that's quite a important relationship if the concentration is equal, because in an exam question you'll be given the pKa of a buffer. You'll be given the pKa of a buffer solution, and if you're given the pKa of a buffer solution, then you can work out what the pH is going to be if you use the same concentration. So that's quite important. Okay, nearly finished. You need to know examples of buffer solutions. Okay, now there's lots of examples of buffer solutions, but for A-level chemistry, the main example, for example, enzymes are very pH sensitive, so there's buffers to minimize change in pH in enzymes. The one you need to know for A-level is controlling blood pH. Controlling the pH of blood. Okay, blood needs to be maintained blood shouldn't go between, it should be between 7.35 to 7.45. Ideally, blood should be pH 7.4. And it's a mixture of buffer systems that maintain the pH of blood. And there's several buffers, but the most important, and this is for A-level chemistry, the most important one you need to know is the carbonic acid, H2CO3. It's called carbonic acid. Carbonic acid is a weak acid, and it will form the hydrogen carbonate ion. Hydrogen carbonate ion. And so this is a buffer system that controls the pH of blood, and it works on exactly the same as what we mentioned before. Okay, so if you add some acid, if some acid goes into the blood, then the concentration of H plus increases, the concentration increases, and the position of equilibrium will move to the left to minimize the change. Okay, but there's a lot of carbonic acid, that's okay. And then similarly, if there's an alkali, the alkali will react with the H plus to give water. The acid concentration will therefore decrease, and the position of equilibrium will move to the right. Okay? Most materials in the blood are acidic. Okay, so if most materials in the blood are acidic, this is our main issue. Okay, so that means position of equilibrium moves to the left, means we have more carbonic acid. And in biology, you do this a lot more complicated. It's more complicated, but I'm going to simplify it. If you have carbonic acid, H2CO3, then there are enzymes that can convert this into CO2, aqueous CO2. This is very, very simplified version. Carbonic acid can be converted in CO2, aqueous CO2, and then in the lungs, the aqueous CO2 in the lungs can be converted into gaseous CO2. Okay, so if you have a buildup of acid, then heavy breathing, like when you're doing exercise, when you have an exercise, you can get your pH of your blood can become more acidic. With heavy breathing, you will release more. It will remove the CO2, which will then push the equilibrium to the right, and therefore will use up more carbonic acid. So if through exercise you have an increase in H plus in acid, then by heavy breathing in exercise, you can remove the CO2, and that will push the equilibrium, so use up more carbonic acid.